Okay, folks, good morning. Any questions? All right. So we're getting closer and closer to the end of the semester. So this is what's going to happen. Next week, obviously, we won't have any classes because of the Thanksgiving break. Then after that, we only have 1 week worth of class. So then after that, we have the finals. The week that you come back from the break on the Tuesday, which is our next session, basically, we are going to have a quiz number 7, the last quiz. And then the week after that, if you choose to take the final test, the Wednesday, I think it's like 10:30 a.m. or so, in this very same room over here, we are going to actually have our final exam. Now, I've had questions about the final, what the format is, questions like that. There's going to be 3 problems, and each problem is almost like a quiz problem, so you could expect 3 times 15 minutes, 45 minutes to an hour of a final test. And remember, taking the final is kind of optional in a sense that if you have done really good in your quizzes, you can argue that I'm going to get an A anyway, so I don't really have to take the final. Not that I'm discouraging you to take from taking the final. However, I've had questions like, I have really messed up one of the quizzes and the rest of the quizzes that I have done are great. Can I take 1/3 of the final? That's the answer is no. Either you take the entire test or not. So technically, the way I look at your final grade, there is a file over here. You can try it out yourself and see what grade you are going to get. Oh, this is not the one. It says calculate your grade. Okay. So you have 7 quizzes and a final. So the final is out of 30. So if you, for instance, take 27 out of 30, there's going to be a 9 and 9 and 9. This is as if you have had 3 quizzes, and each one of these quizzes you have got a 9, something like that. So if you only take 1/3 of the final, these grades are only going to be, for instance, 3, 3, 3, something like that. And the attendance is 5 points, and total is 70. So what I do is I look at from here to here, your 7 quizzes plus the final is equivalent to 3 quizzes, so the total of 10 quizzes. And then I look at the best 7 of them, basically. So if you look at this total over here, I look at the lowest 3 grades that we have had in that block, and I just cut them out. So this could be your final. So you don't have to take the final, then it's going to be 0, 0, 0, and those are the numbers that are going to cut out. Or if you want to improve your grade, for instance, if you have missed, for instance, 1 or 2 or maybe 3 quizzes, then you can do that. Then attendance has 5 points. I don't really have the compiled numbers for all of you guys because this class is still going on. I'm very hesitant about announcing that, hey, you particular student are going to get 5 points out of 5 for the attendance because we still have a week worth of classes going on. And but I will try to do that as soon as I can. So hopefully, before even the week of finals start, after our last class is done, I will upload everything on Blackboard so you can take a look and see whether you really want to take the final or not. All right. Any questions about the final? Yes.
3 problems cover the whole class, or they just be 3 different chapters?
Okay, good question. Is the final comprehensive? Usually it is. I wouldn't say it's like 100% comprehensive, but I would say it's about 70 to 80% comprehensive. I'm going to send you a list of topics that are going to be covered in the final. And as I said, this list of topics could basically cover up to 70 to 80% of the stuff that we have covered so far. So I would say it's almost comprehensive. Yes?
How many sheets?
Oh, the equation sheets, you can have, let's say for each quiz you have had prepared 1 equation sheet, right? So you can have up to 7 sheets because we have had 7 quizzes. Okay, so if you want to keep those sheets, you can do that.
Yeah, you know.
All right, other questions? Okay, so this was all about the final. Again, this file is already on Blackboard. You can play around. Also, as long as Blackboard is open, I would like to remind you guys that I've actually added a bunch of more simulation files towards the end. One of them is the PWM simulation models. I showed this in class at some point. A few of you were interested, so the files are there, although the files are actually being created for my own purpose. So if you open up the file, it might be a little bit confusing. You may not figure out what's going on. In addition to that, I've also uploaded some soft switching simulation models, which we are going to actually look at today. One of them is the zero current switching buck converter, and the other one is the load resonant inverter. As you can see, each file is uploaded twice. One of them is with the extension of SLX, and the other one is with the extension of MDL. I don't know, this is like a newer version of MATLAB. When you want to save a file, it asks you whether you wanted to save it under SLX. I don't honestly know what the difference between SLX and MDL is. Old versions, you can always save your file as a model, MDL kind of a file. So I have put both of them over here. And in these simulation files, you need to have Plex. And this is not a standalone Plex. This is like a plug-in Plex that opens up like a toolbox in Simulink. And I've been told that most computers in the computer lab have the capability of opening those files. If you cannot open the files using those computers, let me know. Then we have to figure out some way that you can actually open them. All right, any questions? Okay. So we are still on covering chapter 9, soft switching techniques. We actually looked at two particular topologies in details. One of them was this one over here, which is called the zero current switching buck converter. And then there was another one which was called the zero voltage switching buck converter, which was basically this one over here. There's not a significant difference between them. In both topologies, you are adding an extra resonating cap and an extra resonating inductor to achieve your original goal. And then on the right-hand side of these two circuits, pretty much everything is the same. You have a freewheeling diode, and the main inductor, and the main capacitor, and the output load. Both of these topologies are called resonant switch converters. They're categorized under that category, and the reason is you're adding these resonating components around your active switches and diodes in the system. And then later today we are going to look at another way of doing things, which is called like a resonant load converter or something like that. In that case, you're adding the components around, the resonating components around your load. Now, I've already analyzed this one, and basically the way this thing operates is when we close this switch, this diode is still on. And technically what happens is you are applying the input source across this resonating inductor. So the current of this resonating inductor rises. And this current is the current of the switch as well as the current of the source basically. And at this particular point, this current reaches I out. So all of these topologies, you assume that your inductor is relatively large, so the current is constant to get rid of the dynamics of this inductor and the output cap, until it reaches I out. And then what happens is then the diode turns off, and we have like a resonance between this inductor and this cap. So there is a resonance thing going on over here, and that's pretty much it. And then the diode kicks in, and that goes all the way to the end of the period. Which is this current over here. So as you can observe, among other soft switching features, you can argue that we turn the switch on and the current is not jumping, it's just gradually rising. And also at turn off, the current is coming back to zero, and we are monitoring the current, and therefore as soon as the current has returned back to zero, then we can turn the switch off. So we have ZCS here and there. So basically here and here we have ZCS for the switch. All right. So I have developed a model. So I just kind of review this to actually go back to that model and then show you what is going on. Just a simulation model. And the model is here. Let me see if I can make it a little bit smaller. So this is a classic Simulink kind of a block diagram. And you can see, for instance, oscilloscopes over here, and then a bunch of other blocks like a signal generator and a Plex model. So basically my power stage has been modeled in Plex, and then the rest of it I have developed that in Simulink because Plex doesn't have a lot of capabilities. So if you click on the Plex model, you see, again, let me see if I can make it a little smaller. All right, you can see two converters, and I'm just doing a kind of a comparative study. The top converter is just a classic Bach topology. The bottom one is the ZCS Bach topology, and I'm just trying to compare them. As long as the inductors, the main inductors are concerned, they are both identical 100 micro. The output caps are both 30 micro, and the loads are also identical. I think they are 5 ohms each. And the sources are also the same, 20 volts, and the duty cycle that I'm feeding the switch over here has been adjusted that would give me the same output voltage. So the both converters are giving me the same output voltage, which I think is around 12 volts, like 12.2, something like that. If you are curious about this diode over here, it doesn't really do much. It's in the classic converter, I can just take it out and I'm going to get the same result, but that was just because I was just copying and pasting, just the diode appears there. The switch that I'm using is an IGBT with an anti-parallel diode. You may choose to use a MOSFET, which does the exact same thing, or you may choose to use an IGBT without the anti-parallel diode, and we may actually talk about it a little later. The other thing that you may notice is I have this relatively large resistor over here. It's like 10 kilo ohms. Now, I had to add this resistor. You may come up with a better way of avoiding the addition of this resistor. This resistor technically is not doing much in the system because it's a relatively large resistor. It's 20 kilo ohms compared to 10 kilo ohms compared to the load that I have, which is only 5 ohms. So I can argue that the current that is passing through this resistor is almost zero or negligible. However, what it does is when the current of this inductor returns back to zero and I'm about to turn the switch off, if there is a little bit of a time delay in the software creates an error that I am actually turning the inductor current off, I'm opening the switch and I'm forcing the inductor current to go to zero. It's very, very close to zero. It's not an absolute zero, and the software does not recognize that. So in order to avoid getting that error, I've added this resistor over here. In case I open up the switch, there is an extra path of conduction for the inductor. So a lot of times when you face a problem like that, just add a very large resistor. It doesn't really do much in the system, but it tricks the software and provides an extra conduction path. The resonating inductor is over here, 5 millihenries. The resonating cap is over here, 0.5 millifarads. And I have already run this, and let's take a look at some of the waveforms. This is our, okay, I forgot what it is. This is our inductor currents, these 100 microhenry currents. You can see they are pretty much the same. The red one is the top one, the classic converter, and you see the classic pattern of I turn the switch on, the red curve ramps up, I turn the switch off, the diode conducts, and it ramps down. The blue one is the resonating one. I can see the behavior is a little bit different. And the other thing is, in all of the analysis that we have made, we always assume that this inductor is almost like a constant current source, and you can see over here is actually not. You can see, especially for the resonating case, which is the blue one, it varies from 1.8 amps all the way up to 3 amps. So there is fluctuations in this. Either you may want to say that I'm going to make this inductor larger and larger, so the ripple is going to shrink, or you would say I'm still happy with the assumption of that this current is almost a constant current source. It makes a little bit of a difference in your analysis, not a significant difference. All right. The output voltages, again, I have adjusted the duty cycle of the top one to give me the same output voltage. You can see that they are both creating an output voltage of around somewhere between 12.25 to 12.3 volts. One thing that is noticeable is that the resonating inductor, which is the blue one, gives you an output voltage that has a slightly larger amount of ripple, and that's again understandable because there is a lot of resonance going on in the system. Input current, basically the current that we are drawing from the two sources. So far you can see the waveforms are almost the same, but if you focus on the input current, you can see they are drastically different. All right, so the blue one is the resonating one. So remember, we turn the switch on, we have a straight line at the beginning for the resonating inductor current to rise, then we have a resonance going on, and when the current returns back to zero, we open up the switch. So we have seen this in that slide that I just drew. And then the red one is just the classic buck converter. You open up the switch and the current of the inductor ramps up, and the current of the switch and the current of the inductor are the same. The thing that you can note over here is, in terms of RMS value or in terms of utilizing your source, the red one, which is the classic buck converter, is better. You can see that you are using your source in a wider window compared to the resonating one, that the utilization window is very small. And in order to compensate for that, you can see that the peak current of the resonating one goes as high as about 8.25 amps versus the classic buck converter, the peak is only 3 amps. So when it comes to conduction losses, the blue one, which is the resonating one, is going to exhibit more conduction losses in the system. So you are improving your switching losses, but probably you are adding more to your conduction losses. So switching losses are reduced because I'm not having a jump over here and I'm not having a jump over here. I'm actually having a smooth transition from zero up and down. So switching losses have improved. The voltage of the resonating cap, I don't have a resonating cap over here, so I don't really compare anything against anything. I'm just focusing on the voltage of the resonating cap, and we have seen this in our analysis before. This is when the diode turns off, the resonance starts up to this point. Then beyond this point is just the output current, which is discharging the resonating cap, so we have like a straight line over here. So we have seen this before as well. What else? RX current. So I said I'm adding this weird looking resistor over here, which is not actually part of the converter, and it's a relatively large converter. In order to prove my point, I'm actually looking at the current of this resistor, making sure it's not really doing much in the system. Well, obviously at the beginning there is a transient going on. If you neglect that, you can see that this current is almost basically zero. So actually this resistor doesn't really interact with the normal operation of the system, but plays that trick of the software that I'm opening the switch and this switch is placed in series with an inductor. The inductor current is the same as what we just saw, the input current, and you can see it looks like this. Now these blocks, the command is coming from the Simulink environment, and I'm also measuring the current and I'm actually sending it to the Simulink environment. So if you look at the Simulink environment, I have a control logic over here. You may spend more time and actually develop a better logic. My goal was not to optimize this logic, but anyway, what's happening is this signal that is coming out is the measured current of the resonating inductor. And remember, we want to watch this current, and whenever it turns back to zero, we want to turn the switch off. So this block is actually looking at the sign of this current, like is it positive, is it negative, so we can detect the zero crossing point of this current. and there is a little bit of a signal manipulation over here, and ultimately this determines the reset point of this SR latch. MATLAB calls it an SR flip-flop, but I don't think it's a flip-flop because there's no clock going in, it's just a latch. And remember, the SR latch is, if you activate the set input, the output is set to a particular value. If you activate the reset one, it just resets back to 0. So technically, I can have a signal generator over here which marks the beginning of my cycle. As soon as this signal generator gives me a short impulse, I'm setting my SR flip-flop, SR latch, and I'm saying, okay, the cycle has started. Whenever the current returns back to 0, I can reset this flip-flop or latch and say, hey, the cycle is over, and you have to turn the switch off, basically. So the output of this thing is actually going back to the Plex module as the gate command, basically. There's a little bit of a logic over here. This is just to overcome the startup procedure. Basically, the problem that we have with this thing is, linguistically, it's very easy. You can say, okay, when the current comes back to 0, turn the switch off. However, the current of the inductor is going to remain at 0. If there is a little bit of a noise in the system, you are going to have a lot of false triggering over here. There's going to be a lot of trigger which you don't really care, but the software cannot ignore. So actually, there is a little bit of an extra circuit over here. And for this very same reason, the simulation is a little bit slow because it calculates a lot of, unnecessary points at which, let me actually run it and you can see. It's relatively slow, and if I zoom in, this is the resonating inductor current. You can see there's a lot of calculation going on. Then the resonance is very easy because the current is positive. So whenever the current is remaining at 0, it does a lot of calculations. And if you zoom in, actually you can see all those calculations. The current is supposed to be at 0, but the software doesn't understand it, so it does a lot of math over here to figure out what exactly is happening to this signal, which is supposed to be 0 anyway. So if you see that your simulation is hung, it's probably sometimes for that. If you are curious about adding or not adding this diode, let me just bypass this diode, see what happens. Okay. If you are using a MOSFET, there is definitely an anti-parallel diode over here. So when your current returns back to 0, let me go back to, okay. Here, when we were doing this analysis, we said, okay, the current returns back to 0. The current returns back to 0, and we turn the switch off, and the current remains at 0, stays at 0. However, if you have a diode over here, for instance, you have a MOSFET over there, basically, so the diode is always there, the current doesn't really remain at 0, it actually gets negative and continues its oscillation, something like this. And then comes back to 0, and then by then you have turned the switch off, therefore it's going to be 0. So in order to avoid this little basically negative hump over there, you can add another diode over here to avoid that. So the good thing is you are not sending any energy back to your source, but the bad thing is you are adding a diode to your input current, therefore the losses associated with this diode are going to be introduced to your system as well. So let me remove that diode and see what happens. Oops, I don't know what happened. Okay, so I'm removing the diode. Now if you run the simulation and look at the current, you can see that the resonance goes beyond the cross point of the search, a cross point of 0, and you actually have a little bit of a negative hump over there as well. So the role of that diode is basically eliminating that thing. If you use an IGBT without the anti-parallel diode, you are good to go. You don't really have that diode because the IGBT does not support negative current. But if your IGBT has the anti-parallel diode, again, you're back to the problem that you have with the MOSFET. You will still have to add your diode as well to actually eliminate this negative hump over here as well. But I don't think and I think it's going to actually affect your output voltage as well. Let me just check. Output voltage. Now you can see your output voltage is smaller than where it is supposed to be with the same duty cycle. So that's actually why you add that diode. Any questions? All right. So this is on Blackboard. If you want, open it up and run it and basically see what's going on. And again, a disclaimer over here. The logic that I have over here is a little bit crazy. I was just trying to spend as little amount of time to achieve the goal. So basically what this edge detector does is when you're on the falling edge of the polarity of the current, you reset your latch, but at the same time it resets at a lot of false time. So actually I have two external power signal generators over there. One of them is if you turn the switch on and the current never returns back to zero, you wait a little bit and ultimately you turn the switch off. That's this guy over here. And the other one is as soon as you turn the switch on, there might be a zero crossing, undesired zero crossing, like a noise or something, and then it false trigger itself. So this second one is actually turning the switch on and at least wait for 30% of your duty cycle and ignore the zero crossings for the current during those times. All right, so this was all about that. Any questions? Okay, so we are going to continue our lecture now. So now we are going to move on to a new class of converters. And by the way, you may ask, oh, if I have a buck converter and I want to achieve ZVS or ZCS, I know what I should do. What if I have a boost converter or the buck boost converter? What am I supposed to do then? I mean, what is the system going to look like? Well, there are books that are actually explaining in more depth on zero voltage switching other than the buck topology that we have analyzed. And once you do a few of them, you actually see there is a general theme going on, and that's actually what we cover in advanced power electronics. If you have any kind of converter which includes a single pole double throw switch, there are mechanisms of achieving zero voltage or zero current switching for that particular single pole double throw switch. All right. So now we are going to move on to another category of converters, which are this one is called the load resonant converters. The reason that they're called load resonant converter is because the resonating components are added around your load. So basically, we have this resistive load that we are trying to deliver power to, and we add a resonating cap and a resonating inductor in series with that, this particular case, and then the rest is just an H-bridge. Okay, doing this is not necessarily for the sake of achieving zero current switching or zero voltage switching. Actually, sometimes you do this. You can take advantage of this resonance that is going on between LR and CR to get for instance, a waveform of current or voltage which is very close to a sinusoidal form. Technically, we have seen this topology before. If I bypass this cap over here, or short it, we are coming back to the topology that we studied, the very first topology that we studied when we talked about inverters. I think it was somewhere around here. Okay. If you remember, the very first time we talked about inverters, we used an H-bridge over here basically. We used an H-bridge, and the load of this H-bridge was a resistive load, and in series with that we placed an inductor. This one that we are about to analyze is nothing but adding an extra capacitor over here, basically. And if you remember for this topology, for instance, our output current was like an exponential term, so it was actually going, we turn switches 1 and 2 on, we apply positive VDC across the load, and the current rises following an exponential pattern, and then we turn the other two switches on, we apply negative Vn across the load, and the current actually falls down, again following a very similar exponential pattern. So as you can see over here, we have managed to feed our load with an AC current, but if the objective was to create an AC current that is sinusoidal, it does not look like a very good sinusoidal waveform, and we looked at total harmonic distortion and stuff like that. So we are kind of revisiting this issue with adding an extra, basically, cap over there. Okay. So what happens is the switching pattern is the same. So technically we are, for 50% of the time, we turn S1 and S2 on together. In other words, if you look at the voltage of point A with respect to B, when we turn S1 and S2 on, the voltage of A to B is actually your Vn. Then for the remaining half of the cycle, we turn S3 and S4 on. And obviously turn off S1 and S2, but turn S3 and S4 on. And in that case, VAB is the negative of Vn. So the switching pattern is basically the same. So if you monitor VAB, it looks like a square-shaped signal. All right? So this is Vn, and this is negative Vn. All right. Now we want to see, okay, if you have a square-shaped signal applied to this inductor in series with this cap, in series with this resistor, what is, for instance, the current going to look like? So technically, you're reducing down your analysis to having a voltage source that is a square shape, and this voltage source is applied to L and C and R. Okay, something like that. You can eliminate all of your switches. So one thing you can do, for instance, you can look at, we have done this before, the Fourier analysis. You can break down your periodic input voltage waveform to a bunch of sine terms, and then look at the response of the system to each individual sine term at each individual frequency, and then in the end, add them up all together. As it turns out, this impedance that we see plays a very important role. So basically, okay, let's call it LR and CR and R. So basically, the impedance that our source sees over there, which is basically plays an important role in terms of what our current is supposed to look like. So ultimately, we want to see what kind of current the system is drawing. So actually, let's plot this impedance and make some arguments. I have actually a plot over here. Maybe I should plot it again here. Okay. So impedance is a complex variable. I'm looking at the magnitude of this impedance, which is a real number now, normalized by load. Okay? And on the x-axis, I'm actually looking at omega normalized by omega naught, and omega naught is the resonance frequency between LR and CR. All right, something like that. So I'm actually using a log, basically a scale. So I'm sweeping like a 100 range, and again I have a logarithm scale over here. So if you plot this, you're going to see, for instance, well, first of all, if your omega, which is your switching frequency, is exactly the same as the resonance frequency, what happens is the inductor, the impedance of the inductor and the impedance of the cap kind of cancel out each other. So all you see is just a purely resistor. That's why your impedance is 1. At omega equals to omega naught, your impedance is just 1. Okay, your Z is reducing down to an R. But obviously, if you go beyond this, your impedance gets larger because there is an inductor and there is a capacitor at high frequency. The inductor is the dominating part. At lower frequencies, the cap is the dominating thing. The other thing is the way this actually curve looks like is dependent on the quality factor, which is defined as, okay, let me write it this way. It's easier to look at it this way. The characteristic impedance over R. Remember, the characteristic impedance was the square root of LR over CR. Then if you divide that or normalize that by R, that's called the quality factor. All right. Now, if the quality factor changes, then you can see you can actually argue that you're going to get different curves. For instance, this particular one that I drew is for the case that the quality factor is 1. In other words, the characteristic impedance and my load resistance are the same. However, if I increase the quality factor, you can actually get different responses. All right. This is, for instance, for quality factor of 100, meaning that the characteristic impedance is 100 times larger than your load, your resistive load. Why does it matter? Basically, what this is signifying is, if my quality factor is higher, there is like a little narrow window over here. It's like I'm creating like a notch filter. In that very particular frequency, my impedance is very small, it's just R. And if we go a little bit above and below that frequency, my impedance becomes actually a very large number, something like that. So you can actually, when it comes to the design of this converter, finding the right value for LR and CR, you can play around with this quality factor and make your, for instance, your notch filter a better notch filter by increasing that. Also, whenever I'm looking at a complex variable, I was just looking at the magnitude. I also have to look at the phase, basically. So this is again omega over omega naught, 0 degrees, negative 90 degrees, and 90 degrees. Okay. So with the same argument, when my switching frequency and resonance frequency are the same, L and C cancel out each other, so I have just a number with a phase of 0. If the quality, ultimately the phase is going to grow to 90 degrees if the frequency increases, because I'm going to have a dominating inductor. The phase is going to go to negative 90 degrees if I reduce the frequency, because I'm going to have a dominating capacitor. And again, quality factor has an impact on how this curve looks like. If I improve the quality factor, this is going to get steeper and steeper. Oh, something like that. So if the quality factor is high, a little bit higher than the resonant frequency, I have a very dominating inductor, and a little bit lower than the resonating frequency, I have a very dominating capacitor, basically. That's how you can do it. There are different ways of describing the quality factor. Let me just write them over here. One of them is omega R naught LR over R, which is the same as, if you happen to have omega naught, you can argue that this also gives you the quality factor. All right. So having this in mind, I can actually break down the components of my output voltage. So technically, I'm saying that I have a system like this, and the source to this system is a square-shaped, constant frequency kind of a voltage signal, which is this one over here, going from plus V in to negative V in symmetrically. and I can look at the Fourier series components of this signal. Let me call it VAB, and note that A and B are these points, A and B. All right, so VAB would look like, we have done this before, only odd harmonics appear over here, and that is 4Vn over n pi times sine of in omega t. All right, and now each one of these particular frequencies are going to hit this impedance, and depending on the quality factor, you can write your output voltage to look like this. Basically, you have a resistive division over there. So Zn is the impedance evaluated at the nth harmonic, the magnitude, times a sine function with a little bit of a phase lag, which is the magnitude, the phase angle of your impedance evaluated at that particular harmonic. Now, if you expand this, you will get equations like this. Minus okay, so this is the, I'm sorry, wait a minute. This is just covering this part of it, basically. This is the magnitude of the nth harmonic in your output voltage, okay? So this is how it's going to look like, not the phase angle, just the magnitude. And then you can rewrite this equation in another way, which is to bring in the quality factor, basically. All right, something like this. And you can argue that if I just excite the system at exactly the resonating frequency and my quality factor is good, I can argue that all of the higher order harmonics like third and fifth and stuff like that are going to just disappear, and I will only have a very good looking purely sinusoidal signal in my output voltage. In my by the way, the output voltage is defined as this one over here. All right, the voltage across your resistor. We can argue that your current is going to be a very good purely sinusoidal current. All right, so I have actually some notes over here. Let's go through that. So looking at this equation that I just wrote, and if you choose omega to be equal to omega naught, omega is the frequency of my source, that square-shaped source, which is determined by my switching frequency. So if I select them to be equal and the quality factor is large, then the fundamental harmonic in my output voltage looks like this, 4Vn over pi, and the rest of the harmonics are going to be 0. So I can argue that my output voltage is almost is going to look like a sinusoidal signal. And let's say this was your original objective, to have a sinusoidal output voltage, then you can actually achieve that. So looking at a bunch of waveforms, let me draw the waveforms down here. So VAB is a square shape. Okay, and then V out is going to be sinusoidal. All right, under those conditions. And by the way, V out and I out are the same, basically. And for instance, if you are focusing on a particular switch, for instance, you are, for instance, looking at this particular current of switch number 1, it is going to look like something like this. Remember, switches 1 and 2 are on during the first half of your period, which is providing Vn in VAB. So the output current and the switch current are going to be the same. Here, these switches are off, no current, and then again, current, and then no current. So you can argue that if all of these stars, align in the sky, you can argue that you have zero current switching at the turn on of your switch, as well as zero current switching at turn off of your switch. So not only you generate an output current or an output voltage that is almost sinusoidal, if that was an important, requirement, and not only you did that, you have also achieved zero current switching at turn on and turn off of your switches. Therefore, you have improved the efficiency just a little bit. Let me also draw the voltage drop across your switches. So we are looking at basically this voltage waveform. Okay, obviously in the first half of the period, these two switches S1 and S2 are on, so there is no voltage there. And then we turn them off, S3 and S4 are on, therefore this jumps to Vn. All right, something like that. So you can see you don't have ZVS for the switch, but you have ZCS for the switch. And actually, ideally, you can argue that I don't even need those 4 diodes, unless they are there just because you bought switches that have diodes. You can argue that there's no way for the diodes to conduct. However, this is a very, very tough thing to do, because remember, all of these waveforms are assuming that our frequency and our switching frequency and the resonance frequency are exactly the same. So remember, this is T, and omega is 2 pi over T. And omega naught is, all right? So this was one assumption. The other one, quality factor is large. All right. Now, what if you violate this requirement? For instance, you choose a switching frequency that is, for instance, a slightly different than the resonance frequency. For instance, you could not accurately measure the value of your inductor or the value of the cap, or you measured them and you programmed the system so that they would follow that. But however, as your system was running, for instance, your cap got a little warmer, and therefore the value of the cap changed, or the value of the inductor changed because of the aging, for instance, thing, and therefore you are not there anymore. You are just drifted. You have just drifted a little more. So now if we drift a little bit from the resonance frequency, however, Q is still large. All right, what happens is the phase angle of the impedance is not 0 anymore, because if you drift just a little bit to the left or to the right, you can see there is going to be a huge phase angle between your impedance, for your impedance basically, which is actually your shift. So basically now the waveforms are going to look like this. you're still generating a square-shaped output voltage, VAB voltage. Let's not call it the output. And the output voltage, which is the voltage across the resistor, is still sinusoidal. However, it has a little bit of a phase shift. All right, something like that. So there's a little bit of a phase shift over here. And because of this phase shift, you will definitely need the diode. So if I actually look at what's happening to here, over here, the current, the output current is negative. However, the conduction path should be in a way that S1 and S2 are conducting. So basically, in that particular mode, this is what's happening. The current is negative, but the switch hasn't really, the IGBT does not really support negative current, so the current is flowing through the diodes. All right, so you can see in this particular mode, D1 and D2 are the ones that are on in this little area over here. Then the current changes its polarity, and if you have already done a good job and turned the switches on, now, so this is actually the current over here, now the current changes its polarity, so now it can actually flow through the switch. If you have turned the switch on, goes through the load, and then follows through this other switch. So now you can see that S1 and S2 are going to be on. And how long is this going to last? As long as VAB is VN, or during the first half of the cycle. Now you change the cycle and basically turn these two switches off. Now there is a positive current going on, but you have turned these switches off. So basically that positive current, what it does is, by the way, I forgot to draw this diode over here. So that positive current, what it does is it finds this diode to flow through. All right, something like that. So now we have D3 and D4 on. And then, if you have done a good job, turn the switches on, we will have S3 and S4 on. So now you can see that if you drift a little bit from the resonance frequency, you definitely need the diodes because they are going to play an important role in terms of commuting from one mode to the other. Now in this particular mode, if you are interested in drawing the switch current, switch 1, by the way, by switch 1 I mean IGBT1, for instance. Okay. So the switch is on from here. And this goes on here as well. So you can argue that for this particular case, if you are interested in soft switching techniques, you only have ZCS during the turn on of your switch. But again, you can argue you also have ZVS over here. So let me just write it down and explain why. ZCS and ZVS for IGBT1. The reason that you have ZCS is obvious. The current is actually crossing zero. So that's zero current switching. The reason that you have ZVS is because during this, right before that, for instance, right here, D1 was on. And if D1 is on, ideal diode, no voltage drop across the diode, that means the voltage across the switch is almost zero, so you also have ZVS here as well. So that's why you have both ZVS and ZCS for the diodes. And finally, this is going to make it a little bit clear, voltage drop across IGBT1. It's 0. So you can see the voltage is 0 while you're turning the switch on, so you also have ZVS, basically. And so you have something like this. All right. So so this is how it goes, depending on at what switching frequency you are actually running the show. Your system could be intelligent. It could be adapt its own switching frequency with respect to the resonance frequency of the system, meaning that you can actually add sensors to the system, monitor at what particular time your current is going back to zero, and for instance then turn the switch on and off to get the action. And these are all okay, let me just write it down. So remember, these waveforms were all under the assumption that Q is still large. Now what if Q is not large? For instance, you have a variable load. On one end of the spectrum it gives you a large quality factor. On the other end of the spectrum it does not give you a large quality factor. In that case, not only you are going to have the first harmonic as the dominating harmonic, you will also have, for instance, the third harmonic and the fifth harmonic, and there's going to be a little bit of an extra distortion in your waveforms. Okay. So this was all about having an inverter which does two things. Provides a little bit of a soft switching for you, ZVS and sometimes ZCS and sometimes ZVS, as well as giving you an output voltage or output current that is closer to a sinusoidal waveform compared to that exponential waveform that we had for the non-resonating one. Any questions? Okay. So since there are no questions, I have this topology simulated. So let's look at the simulations.
Actually, I just have a question.
Okay.
So, like, let's say you're using a 60 hertz waveform.
Okay.
You'd have to exactly size those L and C to get the correct.
Yes, you're right. So technically, when it comes to finding the size for your L and C, remember you have two equations. One of them is if your objective is to generate a 60 hertz kind of an output current waveform, L and C should satisfy this equation. So we are talking about relatively large L and relatively large cap. And also, if you want your quality factor to be high, and you know how much load resistance you are or how much power should be delivered to your load, you have an idea about your R. So L and C also should satisfy this. That means L should be relatively larger than C. Okay? So usually in these topologies, your cap is a relatively small cap, but your inductor is a relatively large inductor for this very same reason over here, that you want to have a large quality factor. Yes?
Also, which one is more efficient, this topology or the previous one?
The previous one, I have not done extensive efficiency analysis. I would say each one has advantages. Like over here, you can argue that you can have ZVS and ZCS. And by the way, the thing that I keep forgetting about is ZVS and ZCS or soft switching in general is not always about efficiency. Sometimes it's the matter of noise. If you have a sudden jump in a particular current or a particular voltage, that means di over dt or dv over dt is relatively large. That means it can couple with some parasitic components in the system and emit noise in your system. However, if you achieve ZVS and ZCS, the noise is going to reduce. So definitely in terms of noise, this topology, the new one, is better. In terms of switching losses, it is also better because it can achieve ZCS and also ZVS sometimes. In terms of conduction losses, I don't know. I have to do some analysis. I would say this could be a little bit worse in terms of conduction losses. So it depends. The efficiency depends on that sweet spot that you have improved your switching losses, but your conduction losses have got deteriorated a little bit. But at the same time, the overall net effect is your efficiency has improved. So I would say you can design a system like this, which could be more efficient than the previous one, or you could design one which is less efficient, unintentionally less efficient than the previous one. All right, other questions? Okay, so let's look at some simulations. And again, as I said, this other file is also on Blackboard. Whoa, okay, where are we? Okay. So this particular one, because I wasn't doing anything fancy in terms of controls, everything is, this is your simulating environment. There's nothing in it except for the Plex block. So if you just click on the Plex block, this is your topology. You have a DC source of 100 volts over here. And then we have this L and C and R. And as Steve asked, you can see that L and R, or L is relatively large, is 50 millihenries. And C is relatively small, 140 microfarads. This would gives me a large L over C, or a large characteristic impedance, or a large, basically, quality factor. My load in this particular case is 10, and I'm just running this and looking at a bunch of simulation, bunch of signals. The VAB that I've labeled over here is actually provided basically here, which is the voltage of this point with respect to the voltage of this point over here, A and B. Okay, I didn't put A and B, I should add it actually over there. First thing that I did was I kind of bypassed the capacitor, just going back to our classic inverter, and I think I've already have the results, and here are the results. For instance, this is your output current, the exponential pattern that we are familiar with. Switches 1 and 2 are on, therefore it ramps up, or doesn't ramp up, it exponentially goes up, and then switches 3 and 4 are on, and then it exponentially comes down. So we have already seen this before, about 4 weeks ago and 3 weeks ago, and now I'm going to actually remove this, or basically add a cap to the system. And now let's take a look. Actually, even before doing that, let's actually look at a bunch of other waveforms. Well, obviously the first one that I looked was the current. Now I'm looking at the voltage of the resistor. They are proportional with each other, no surprises here. And I'm also looking at this particular IGBT's current. You can see even before we had a little bit of a ZCS going on. Okay, so what's going on here? I have 3 curves. The red one is the voltage of the IGBT. It's either 0 or 100. The blue one is the current of the IGBT, and the yellow one is the current of the output current, basically the current of the load, which is that exponential thing. So you can see at this particular point, the IGBT turns on and conducts some positive current, and actually we actually have a little bit of a ZCS over here as well. A zero current switching is going on for the IGBT as well. I'm also looking at the current of this diode over here. So we have 3 traces. The blue one is the voltage of the diode. It's either 0 or negative 100. The blue one is the current of the diode. It should always be positive or 0. And then the yellow one is the output current. You can see over here, we turn the switches off, S3 and S4. Therefore, as a diode number 1 has to conduct this current in reverse basically direction. So I turn on of the diode. You can see there is no zero current switching going on, but at turn off, the current gradually comes down to 0. So I turn off of the diode, we have zero current switching going on, even with the non-resonating one. All right, now let's remove this and have a resonating one. Okay, so let's look at, for instance, the voltage across the resistor. You can argue that this is almost a sinusoidal signal. Let me actually make it a little bit better. Simulation parameters, 1e negative 4 maybe. This is just a time step format that. Okay. Okay. So you can see, you can still see a little bit of a distortion in it, but you can argue that this is much better than those exponential terms, and even you can make this a little bit better. I mean, depending on your quality factor. For instance, if I increase the value of R, remember the quality factor was this, 1 over R. So the smaller the load is, my quality factor gets better, and therefore I'm getting closer. I would get closer and closer to sinusoidal output voltage. I don't know, sometimes it doesn't show. Okay, so if my load, instead of being 10 ohms, was only 1 ohm, I would almost have a very good looking sinusoidal signal. And well, obviously the question is, can you voluntarily change your load? I mean, your load is determined by something else, but let's say if that scenario existed. So this is the impact of your load. So it's purely sinusoidal. The input current is actually the current of your basically source. You can see in this graph it is supposed to be almost a rectified version of a sinusoidal current, but there is a little bit of a distortion over here, and this little bit of a distortion is because my switching frequency is not exactly synchronized with the resonance frequency. There is some rounding error somewhere. But you can, when you implement the system, you can make it a little bit smarter. Instead of predetermining your switching frequency, you can observe the signals in the system and turn the switches on and off based on those to really be synchronized. Let's look at the IGBT over here. Okay, again, 3 traces. One of them, the red one, is the voltage across the IGBT. Whenever the IGBT is off, you see 100 volts. Whenever it's on, it's 0. And the blue one is the current of the IGBT. It's sometimes 0, it's sometimes positive. And the yellow one is the output current. And sometimes the IGBT current and the output current are the same. And you can argue that this is almost like a half rectified, half sinusoidal signal, and then it's 0. You can argue that here the current is almost 0, so we have ZCS at turn on of the IGBT, as well as the 0 current switching at turn off of the IGBT. For the diodes, in this very particular case, diodes do not really play an important role. You can see, again, the 3 traces. The red one is the voltage of the diode, and the blue one is the current of the diode, and the yellow one is the output current. And you can see there is only conduction for the diode, just this little piece of time, and this is because not everything is exactly synchronized. So you still need the diodes if you are not exactly right on target, but the diodes are not really utilized as much. And again, you can argue that when the diode turns on at this time, the current jumps to 5 amps, so there is no ZCS at turn on, but we have ZCS at turn off. And what I forgot about is having these diodes also provide you ZVS at turn on of the IGBT over here. During this little time, the diode is on, therefore there is no voltage drop across the IGBT, so when you turn it on, there is ZVS here as well. Then you can mess around. You can, for instance, say, what if my switching frequency is a little bit not synchronized? We can play around with the Q factor over here. Let me play with the Q. So we decide Q of a load current of 10 ohms. Let's change it to 50 ohms, assuming that you have a variable load. And now you can see, you can actually observe the distortion in a more significant way in your output voltage. So that's obvious that once you change your load in a way that your quality factor is not good anymore, you are going to see a lot of harmonics in your output voltage. And let me bring it back to 1 again in the very good case. So the very good case, you have a very good looking sinusoidal output current or voltage. But now I want to change the frequency a little bit. Let's say my switching frequency somehow is not synchronized with the resonance frequency of LR and CR. Now, unfortunately, I haven't done this in a good way. So let's say instead of 60 hertz, I'm switching at 61 hertz. Well, it's easier to introduce a parameter and just change the value of that parameter, but I haven't really done that, so I'm just doing it the more time-consuming way. All right. You can argue that your output current, or whatever this is, the output voltage, is still sinusoidal, no problem there. However, if you look at this, this, for instance, IGBT current, you can see that the synchronization is actually kind of violated, like the analytical approach that I was doing earlier. At this particular point, your IGBT turns on, and it's ZCS, but because the current and voltage are not synchronized anymore because of this mismatch in the frequency, and remember, I only changed it 1 hertz. It's not a lot of change. It's only like 1/60th of a percent. No, 160th of a percent. And you can see at turn off of the IGBT, you have this sudden jump in the current of the IGBT, so you have actually lost your zero current switching. So as I said, a better approach would be, instead of predetermining your switching frequency should, for instance, measure the zero crossing and then adjust itself according to this zero crossing. So you can actually always can provide zero current switching. For the diode, the same scenario. Remember in the previous case that everything was set and adjusted. The diodes were as if they were not even in the system. They were not really conducting a lot of current. But now if you look at this blue triangle, you can see that, yeah, the diode is actually contributing a lot in the system and providing a commutation between S1 and S2 versus S3 and S4. So at turn on, the diode turns on at the non-ZCS, but at turn off, the commutation between the diode and the IGBT is at zero current switching. All right, any questions? So one note about your quiz for next week, not the week after next week, is the material that I covered today is also included in the quiz. So the materials to be covered in the quiz: buck converter ZCS, buck converter ZVS, and this resonant load converter using an H-bridge basically converter. Any questions? All right. For those of you who are late, I explained how this final thing is going to work. Technically, the final is going to be 3 problems. Each problem is almost equal to a quiz. So basically, it's like as if you're taking 3 quizzes in a row, technically. And if you have done really well, or if you're happy with your performance in the 7 quizzes that you have had in this class, you don't have to take the final. If you are not happy and you want to improve that, then you can actually take it. And the way it works is I break down your final grade, your final exam grade into, divide that by 3. So let's say your final has 30 points. I divide that to 3 segments of 10 and 10 and 10 points, as if your final was 3 quizzes in a row. So I have 7 quizzes in your semester, 3 quizzes in the final, a total of 10 quizzes. Then out of those 10 quizzes, 10 numbers that I have, I pick the top 7 ones and calculate your grade. Now, unfortunately, if you have only missed 1 quiz, the option is not like, oh, I missed the quiz, therefore I want to answer only 1/3 of the final. Either you take the entire final or not. I mean, you can choose not to answer the other 2 problems, but then your grade is going to be 10 out of 30 for your final. When I divide it by 3, is going to be 10 over 3, 10 over 3, and 10 over 3, kind of a grade. Questions? All right. So my goal is, as soon as we are done with our next quiz, for instance, 2 weeks from today, Thursday, which is going to be our last class, hopefully as soon as that class is done, my goal is to update all of the grades on Blackboard so you can make a decision at that point. Do you want to take the final or not, basically? How was your performance in all of the quizzes? And by the way, how was your attendance record? So by then, please hold your emails. Don't ask me, don't send me an email asking what is my grade and stuff like that, because again, we still aren't done with one of the quizzes, and we still have 2 lectures that you may or may not miss. Therefore, I don't really have anything final and solid to report to you at this point. All right. So see you guys after the break. Enjoy your break, and don't forget about the quiz.